In this video, we dive into our study of 308 Winchester case volumes, what we call the bag-o-brass project. Let's start with some background on this project and focus on the importance of case volumes, get into the various aspects of measurement, demonstrate how we make these measurements, discuss results, and then illustrate how you can use this in practice and the takeaways of the study. The ideas presented in this study apply to all manners of reloading. We're particularly focused on precision shooting, which needs precision ammunition. We want to understand and control multiple factors and then optimize these for best performance. Everyone's always on some type of learning curve, but start where you can and drive for improvement. And Accurate Shooter's a good website to get started. If you're building ammunition for competitive batches and high precision work, we have what we call the sensible approach. You simply standardize on the best components, and this will minimize variables and variance, and then you could study and then perfect your loading techniques. What we're doing in the bag-o-brass project is a little different. Several years ago, when we started loading 308 Winchester, we wanted to study and understand the problems and issues that come into play with loading this round. So then we could look at developing measurements and analytical techniques for understanding and solving problems. So bag-o-brass project is simply buying bags of brass at the range or gun shows. And in this presentation, we're focusing on case volumes. It's important to remember everything we're going to discuss here should always be kept in mind. Safety first all the time. Here are the components that make up a loaded round of ammunition. We can think of the cartridge case as a combustion chamber. After the propellant has been ignited by the primer, the case operates into the chamber, but immediately barrel volumes come into play. So propellant performance is tied to the weight of the charge, but also these volumes. This falls under the category of low density theory. Internal ballistic factors interact in a complex way. So in this study, we're just focusing on determining case volumes. We want to measure and study these weights and volumes statistically. We believe this leads to improved understanding of the loaded round performance. Small variances in load density can make a big difference in velocities and variances like standard deviation. One source quotes 1 grain of powder creates about 20 cubic inches of combustion gas. So 42 grains creates about 850 cubic inches, which is about 3.5 gallons of gas. So in reloading, we're dealing with charging weights that range more than 10%. So we think you should look at case volumes when you think about your reloading process. Quick positioning on propellants. Smokeless powder, black powder, and a lot of pyrotechnics precede by what's called deflagration. This is the domain of low explosives that are basically burning, and this moves by a heat wave. In the past, this was pegged at about the speed of sound, but current research puts it at around 3,300 feet per second. It's Mach 3. Detonation, on the other hand, is the domain of high explosives. This propagates by shock wave greater than Mach 3. In this diagram here, in this photo, this is 500 tons of TNT going off. And you'll see the shock wave on the surface of the water, but you'll also see a condensation cloud created by this shock wave. And just for scale, that little thing right there is a naval warship. You might run across the term DDT, deflagration, detonation, transformation. This is where a small amount of powder, high-speed powder, in a large case, cartridge case, may go from burning to explosion, detonation. I wouldn't worry about this too much because this can be avoided by following the load data from trusted publications. For this study, let's agree on measurement units. The grain, abbreviated GR, and on some balances you'll see GN, is a unit of weight. We're going to use it as a proxy for the unit of mass. there's 7,000 grains in a pound. So 1 grain is equal to 0.0648 grams, or more conveniently, 64.8 milligrams. For volume, we're going to use the milliliter, which is 1/1000th of a liter. And for reference, a liter is equal to approximately a quart of liquid. The density of water for all practical purposes is 1 gram per milliliter. And a milliliter is equivalent to a cubic centimeter, which might be abbreviated cc or cm cubed. So 1 cc of H2O is equal 1 gram. In this study, we're going to use grain cc H2O measurement unit for case volumes. So 1 grain cc H2O is equal to 64.8 milligrams. Now, this is the magic. We now have a volume unit from weight. Let's look at a couple of common examples. You can convert grain cc over to milliliters with this conversion factor. Here's 300 Blackout, about 1.5 milliliters, 223 Remington, about 2 milliliters, and the 6.5 Creedmoor and 308 Winchester are comparable cases, and they're both about 3.5 milliliters. But just for scale, you can see the monster that the 50 BMG is, up at almost 20 milliliters of case volume. All powders, including our propellants, are divided solids made up of particles. Sometimes you'll see a term grain size. Back in antiquity, this was related to the grain weight, but it isn't that way anymore. Divided solids are made up of distributions of these particles. We call particle size distribution. Here, an instrument is run that analyzed all the particles in this sample and presents a histogram. As you can see, special methods are needed for measuring densities of divided solids. The first type of density is apparent density or bulk density. This is the powder is fluffed up and is always the lowest density. So think of it like a box of cornflakes. When that's filled, the box is full up, but when it settles and you get it home, it looks like the box is half empty. To measure bulk density, you need devices like the Scott volume meter shown here for making measurement. And this can be used for propellants. We think that most of the quoted values for density are apparent density for propellants. Another type of density is called tap density. Here, the powder is vibrated or tapped to a lower volume, giving a higher density. The type and amount of tapping must be called out. And there are commercial instruments like this one here that give tap density. Here you can see in this cylinder what the bulk density looks like, and after the vibration takes place, you see the result, lower volume, higher density. We think this is a better measurement, particularly for the project we're doing here, to give a more consistent measure for propellants. True density is actually the chemical density of a material. So like a bar of aluminum, you would have a density for that. But this true density isn't used for divided solids like our propellants. Measuring case volumes with distilled water has been a standard and been around for a long time. It's simple to apply, but kind of messy. But the fact that the water density is 1 gram per cc is very convenient. And also the meniscus issue comes into play. So you have to look at some sort of surfactant to reduce the surface tension and get your best measurement. As you'll see as we go through this study, we're much more interested in how divided solids fit into the case. So we want to look for alternate measurements and study these more closely. Well, why don't we just use propellants? First of all, there's large differences between bulk and tap densities. Second of all, what kind of powder you're going to use. There's many different morphologies: balls, flakes, sticks, and tubes. So none of those are particularly appropriate for this study. Also, powders are hygroscopic, pick up moisture, and also solvent evaporation, and be sensitive to temperature and humidity. And just for safety reasons, open handling of powders is not good. You run the risk of flame or static discharge. What we chose is use Florida Gulf Coast white beach sand. This is 99% silica, quartz silica. It's a very fine powder, has excellent tap density performance, very inert, stable, easy to use, and inexpensive. So this is what you'll see coming up next. Measuring case volumes is a two-step process. First, we're going to use graduated cylinders to calibrate our sand to get a conversion factor. So 20 milliliters of sand weighs 31.47 grams, giving us a conversion factor of 1.57. We can now use this conversion factor to find the equivalent grain cc of volume of the case. You simply take the weight of sand in grain divided by the conversion factor, and we get grain cc for volume. The second step is to go through all of our samples. First thing we want to do is baseline prep our cases. We've prepared a video called PounderLabs Part 1 that goes into baselining in detail. So please view that video at your convenience. We want to fire and retain the fire-formed cases. We want to deprime and ultrasonically clean the cases. And we just use a hand paper punch to create little pieces of tape to plug up the flash hole. We weigh the empty case, record case details, weight, head stamp. We tear off the case weight and then tap fill with sand and reweigh the case. This gives us the weight of sand. We then convert this to grain cc and then plot the case volume and grain cc against case weight. Here are the results we recorded, but let's first look at this table. Compound, tap density, published density, which as we mentioned earlier is most likely the bulk density, and the appropriate conversion factor. Here's water, and this is the density in grain per cc. Here's our sand, we showed how to measure that earlier, and the conversion factor. Here's three different powders. Bullseye and red dot are flake type powders, and you'll see what we got for tap density, and then the published density, and the appropriate conversion factor. You'll notice the difference between these two is actually greater than 10%, more on the order of 13%. We explained that earlier. Reloader 15 is a tube type stick powder, and you'll notice a smaller difference between the bulk and the tap density. Also, if you look at these conversion factors, the astute viewer would see that these are less dense in water, it would float, whereas the sand, of course, is greater than 1 and it would sink. We found three different types of characteristic weights for Hornaday. We call Hornaday heavy and then Hornaday batch. Here's Federal cases here, and then the Bag-O-Bass project is a lot like that box of chocolate. You never really know what you're going to get. And in our bags, we ran across cases from Men, which is a German manufacturer. We're going to cast all this in a larger sense in just a moment. In the previous slide, we plotted the samples individually. Here, we've combined all of them together, and you can see the relationship. Case weights range from 155 out to about 185 grains, and case volumes range from about 55 up to almost 60. So the question right now is there a relationship that we can see that comes out between case volume versus case weight? Here, all the individual samples have been brought together into one data set for analysis, and we've fit a regression line to this. And here's the equation, and you'll notice from the coefficient of determination, this is a pretty good fit, given that we've got multiple different samples and given in the limitations of our measurement system. So there's a nice linear relationship. You'll notice, according to this analysis, The SAMI spec of 56 grain cc would mean that the a weight of a case for that would be 178.6 grains. So you figure 56 over here and down. So we have a cluster here, but we can see cases way heavier than that and less than that, but they fit along this line. So we have a predictor for case volume by measuring case weight. We've demonstrated the relationships with the sand, but let's now make this much more practical for the shooter. We're using the same method as we stated earlier, but now we're using relator 15 with our 4 branded cases, and sure enough, we get the same relationship. Light cases here, heavier cases here. It's a nice clean linear relationship, and we have a good fit to the data. But there's several things to note here. Even though we have the same relationship, it's not as accurate as sand. If we take our 56 grain cc SAMI spec, and here we would see that that would mean the case should weigh 167 grains. Well, why is this? Reloader 15 is a large stick type powder and doesn't fill the case nearly as efficiently as the sand, and the sand doesn't fill it as efficiently as water. So what's going on is filling the volume of this space with these different divided solids is a fractal problem. This was researched by a gentleman who turned the turn of the last century named Lewis Fry Richardson, and this effect has actually been given his name. It originally got started with trying to measure the coastline of the United Kingdom, where the length of the coastline is highly dependent on the length of measure that you have to measure it. So the finer and finer the measurement, the more and more accurate you measure the coastline. It's the same process that we have going on here as it relates to case volume. The takeaway is 2 main things. One, we need to always be thinking about understanding case volumes specific to the powder at hand. And all powders are different, plus also even different lots or age of the powder come into play. So we have to keep an eye on this and re-understand this every time something changes in our reloading recipe or loading methods. Is this concern about case volume warranted? Well, you make the call, but let us show you this. Even premium cases have variances. This is a sample of a brand new lot of Lapua 308. We've weighed and histogrammed the weights. The average is 174 grain right here. Well, you might expect a bell curve distribution. So many folks are very surprised to see this sort of affair here. So the actual number of cases that are the average weight is 1 out of 100. But don't be concerned about this, because for something freshly manufactured like this, the manufacturer is probably more concerned with fitting within lower and upper spec limits rather than the average. Okay, so what would you do with this? Well, you could take a look at this and say sort for shooting applications. So we can go plus or minus 1 standard deviation here, which is going to include 68% of the lot, which is 70 out of 100. And this is what you used for your competitive match loads. And then the ones that are heavier and lighter of that are for practice and load development and such. The key takeaway is unless you are weighing and understanding the weights of the brass and the distribution, it's a mistake to think that they all weigh the same. So what does this mean in a practical sense? Let's look at an example. Here's the conversion factor for reloader 15, the powder tap density. We can now use the equation to determine the powder volume from the weight of the case. It's important to remember the work we're doing here is the total volume of the case. So you need to make adjustments based on your load recipes for these percentages. Also, bullet seating depth comes into play, and also once you go into a compressive load, things change again. Note here, Nosler has load data with loaded rounds. They explain how they do that, where they get the case volume, called grains of water, powder charge weight grains, and load density. So you can see an example here for their cartridges and cases and so forth. You can see what the volumes actually look like with water for loaded rounds. Here, this is the total, and you need to make that consideration. Here's an example. So let's say we're interested in loading to 80% of the total unloaded case volume. If the case weighs 175 grains, that means the charge weight of 42.3 grain is 44 grain cc's volume. Now going up just 1 grain, the charge of 42.2 grain is 43.9 grain cc volume. You can see from the table that as little as 1 grain change in the case volume is created by a different tenth of a grain weight. So consider this when you're trying to weigh out 1 kernel of powder, but if you don't understand what's going on in the case volume, you could be off by 10% in what should actually be the equivalent load density. So what have we learned? We've shown there's a relationship between case weight to case volume for the 308 Winchester. We've shown that this is a two-step process. We find the tap density for the powder to get a conversion factor, and weigh the cases and weigh the powder in the cases. Use a simple linear equation to find the case volume in grain cc H2O. This is a first order approximation, but works just fine here. Remember, case geometry plays a hand. These cases aren't perfect cylinders. The outsides have been defined, but the insides have wall tapers and shoulders and neck thicknesses. We've shown that for different types and brands, case volumes can range from under 12% SAMI to over 6% SAMI. And what hopefully you've seen that this technique is easily done with equipment you already have on hand in the reloading room. Maybe just add a graduate cylinder, you already have your balance, and basically you're good to go. And what we're trying to illustrate is applying even simple analytics can give us new insights for performance improvements and making better reloads. And as Jeffrey reminds us, have fun, but please be careful. Feel free to pause the video playback if you would like to look more closely at any of these references and citations. This completes our presentation today, and as you're thinking about subscribing, please look over these important notes and disclaimers. They're here for your protection and ours. Thanks for watching. See you soon.